Hello everybody, my name's Iman. Welcome back to my YouTube channel. Today we're going to be tackling a practice problem set that relates to our lecture on thermochemistry. Let's go ahead and get started with problem number 1. Problem number 1 says, consider the cooling of an ideal gas in a closed system. This process is illustrated in the pressure volume graph shown in the following figure. Based on this information, the process may be blank. So we're given this pressure volume graph that shows the cooling of an ideal gas in a closed system, and the graph's shape is going to help us determine which type of thermodynamic process is occurring. Now, in lecture, we discussed 4 main thermodynamic processes. They include isothermal process. This is when the temperature stays constant while the gas changes volume and pressure. We discussed adiabatic process. This is when no heat is transferred in or out of the system, so the gas cools or heats up without exchanging heat with its surroundings. Isobaric process, this is when the pressure stays constant while the volume changes, and this is in contrast to isochoric process. This is where the volume stays constant while the pressure changes. Now, if you're looking at the isobaric and isochoric processes, their graphs demonstrate a horizontal and vertical line, and that doesn't really match up with the figure that we're given for this problem. So we can go ahead and eliminate those answer choices right off the bat. What we're left with is adiabatic and isothermal. How do we determine if this process is adiabatic or isothermal? Our hint actually lies in the first sentence of this problem. The first sentence of this problem says, consider the cooling of an ideal gas in a closed system. Cooling implies that the temperature is changing. And if the temperature is changing, then it cannot be an isothermal process because an isothermal process is described as a process where the temperature stays constant. So we can go ahead and eliminate isothermal. What we're left with is adiabatic, and this process may be adiabatic, so the correct answer for problem 1 is going to be A. Wonderful, let's move on to problem 2. Problem 2 says, a pot of water at 100 degrees Celsius sits on a heating element and boils. Which of the following best characterizes this phase change process? Now, what's going to help us answer this question is thinking about heating curves. So, when a compound is heated, its temperature increases until it reaches a phase change point. For water, there's a phase change point at 100 degrees Celsius where liquid water boils and can be converted into vapor. Now, at this phase change point, the temperature, it remains constant despite continuous heat addition. And this is because that energy is used to change the phase of the substance rather than increasing its temperature. So let's keep that in mind as we look through the answer choices for this problem. Answer choice A says isothermal expansion. Now, isothermal process occurs at constant temperature. For boiling water here, the temperature remains at 100 degrees Celsius during the phase change from liquid to gas. Now, it is also expanding because as the water is boiling, it expands into steam. So isothermal expansion is a pretty good description of what is happening in our problem. Let's keep that in mind as we work through the other answer choices. Answer choice B says adiabatic expansion. Now, if you remember, adiabatic means that this process is occurring without any heat exchange with the surroundings. This doesn't fit boiling because heat is being added to the water. So we can go ahead and eliminate this answer choice. Answer choice C says isovolumetric heating. Now, this is a process that occurs at constant volume, and this isn't relevant to boiling because the water expands into steam. So this is also incorrect, and we can go ahead and eliminate that answer choice. Answer choice D says adiabatic compression. Now, this kind of process involves compressing the substance without heat exchange. This also doesn't describe boiling either, because there is heat being applied to this boiling system, and also it's not compressing, it's expanding, because water expands into steam when it is heated up to 100 degrees Celsius and it is boiling. So D also does not make any sense for this process. The correct answer for 2 is going to be A, isothermal expansion. And again, this is because when water boils, point 1, temperature remains constant at 100 degrees Celsius while the phase change occurs. Point 2, heat is added to the water, causing it to transition from the liquid phase to the gas phase. And point 3, the volume of the water increases as it turns into steam. Beautiful. Let's move on to problem 3. Problem 3 says pure sodium metal spontaneously combusts upon contact with room temperature water. What is true about the equilibrium constant of this combustion reaction at 25 degrees Celsius? Now, what we're going to use to answer this problem is the following equation that relates the standard free energy change for a reaction to the equilibrium constant. Here, R is the ideal gas constant, T is the temperature in Kelvin, and KEQ is the equilibrium constant. Now, this equation is really important because it allows us to not only make quantitative evaluations of the free energy change of a reaction, but also qualitative assessments on the spontaneity of the reaction. Now here, the greater the value for the equilibrium constant, the more positive the value of its natural logarithm. The more positive the natural logarithm, the more negative the standard free energy change is. And the more negative the standard free energy change is, the more spontaneous the reaction. Now we're given that this reaction is spontaneous, so we know that delta G has to be negative. And again, in order for delta G to be negative, this natural log value of the equilibrium constant has to be a positive value. How do we ensure that the natural logarithm of the equilibrium constant is a positive value? What is the condition? Well, let's start off with the basics. Natural logarithm of 1 is going to be 0. If you want the natural logarithm of the equilibrium constant to be positive, to ensure that delta G is negative, the equilibrium constant needs to be greater than 1. If it was less than 1, delta G would be positive. All right, if it's more than 1, delta G is negative, and that's exactly what we want because we know this reaction between pure sodium metal and room temperature water happens spontaneously. All right, and that means that the answer for problem 3 is going to be D. The equilibrium constant needs to be greater than 1. Moving on to problem 4. Problem 4 says, which of the following processes has the most exothermic standard heat of combustion? A says the combustion of ethane. Ethane has a molecular formula of C2H6. B says the combustion of propane. Propane has a molecular formula of C3H8. C says the combustion of N-butane. The molecular formula for butane is C4H10. And D says the combustion of N-pentane. Pentane has a molecular formula of C5H12. Now, the heat of combustion, this is the amount of heat released when 1 mole of a substance is burned completely in oxygen. It's an exothermic process, meaning it releases energy. Now, in general, the more carbon and hydrogen atoms that a hydrocarbon has, the more energy it will release upon combustion. This is because there are more bonds to be broken and formed during the combustion process, resulting in a higher release of energy. Now, all 4 of our options are hydrocarbons, also called alkanes. And so here, for each of these alkanes, we can determine, based off of our condition, which one is going to be the most exothermic? Which one is going to have the most exothermic standard heat of combustion? It's going to be N-pentane because it has the highest number of carbon and hydrogen atoms, leading to the greatest amount of energy released during combustion. And so the correct answer for 4 is going to be D. Next up, we have problem 5. Problem 5 says methanol reacts with acetic acid to form methyl acetate and water. Based on the values in the table above, what is the heat of reaction in kilojoules per mole? Now, this is a really fun problem because at first glance, it might seem like a math-heavy problem, but it really doesn't require any calculations at all. We just have to keep track of which bonds are broken and which bonds are formed, and remember that breaking bonds requires energy, while forming bonds releases energy. So let's go ahead and draw out this reaction. Here we have acetic acid and methanol. They react together to give us methyl acetate and water. Now let's go ahead and look at acetic acid first. Let's make note of what kind of bonds we have going on here. So we have this carbonyl group, and that carbonyl carbon is bonded to a methyl group, and then it's also bonded to an oxygen that is attached to a hydrogen. It's bonded to this alcohol group right here. Now, most of the structure for acetic acid is preserved in this product right here, in our methyl acetate product. The only difference is that this oxygen in the products is no longer bonded to a hydrogen, it's bonded to a carbon. So let's make note of that. We are breaking an oxygen-hydrogen bond to form an oxygen-carbon bond. Okay, now let's also take a look at methanol. So what we notice for methanol is it has this OH group, and that oxygen is bonded to a carbon. Here on the product side for water, we have that OH group, but that oxygen is no longer bonded to the carbon, it's bonded to a hydrogen. So what's happening here is we're breaking an oxygen-carbon bond to form an oxygen-hydrogen bond. Okay, so what we're noticing here is that 2 bonds are broken. A carbon-oxygen bond between the carbonyl carbon and the oxygen of acetic acid. And then the second bond that's broken is the oxygen-hydrogen bond between the hydroxyl oxygen and the hydrogen of methanol. Now, 2 bonds are also formed. A carbon-oxygen bond between the carbonyl carbon and the oxygen of methyl acetate. And then the second bond that's formed is an oxygen-hydrogen bond between a hydroxyl group and a hydrogen to form water. What you notice is that the same 2 bonds that are broken are the same as the 2 bonds that are being formed in the reaction. We're breaking an OH and an OC bond to form an OH and an OC bond. And therefore, the energy change for this reaction has to be 0 kilojoules per mole. And so the correct answer for problem 5 is going to be A. Wonderful. Let's do problem 6 together. Problem 6 says, which of the following refers to the temperature and pressure at which all 3 phases exist in equilibrium? So this is a pretty easy definition question. Let's go over all our answer choices. I'm going to remind you of the definitions of each, and then it's going to be really easy to solve this problem. So A says critical point. Remember that the critical point is the point at which the liquid and gas phases of a substance become indistinguishable. So beyond this point, the substance exists as a supercritical fluid. This is not what the problem is asking. We can go ahead and eliminate this answer choice. B says triple point. This is the point at which all 3 phases, solid, liquid, and gas, of a substance coexist in thermodynamic equilibrium. This is exactly what this problem is asking, and B is the correct answer. But we're still going to go over C and D. C says deposition. Deposition is the phase transition in which gas transforms directly into a solid without passing through the liquid phase. Again, not what the problem is asking. and D is state functions. These are properties that depend only on the current state of the system and not on the path taken to reach that state. So examples include Gibbs free energy, entropy, enthalpy, temperature, volume, pressure. This is not what this problem is asking either, so we can eliminate D. Again, the correct answer for problem 6 is going to be B, triple point. Problem 7 is up next. Let's read it together. Problem 7 says a 10-gram sample of water is brought from 40 degrees Celsius to boiling, and it is completely boiled to the gas phase. Which of the following expressions represents the total amount of energy required if the final temperature of the vapor is 100 degrees Celsius? We're also given the heat of vaporization of water. That is equal to 2,260 joules per gram. Again, here for this problem, we're going to rely on our heating curves. Keep in mind that when a compound is heated, its temperature increases until it reaches a phase change point. So for water here, this is going to be the boiling point, which happens at 100 degrees Celsius. Then, at this phase change point, the temperature remains constant despite continuous heat addition. And again, this is because that energy is now used to change the phase of the substance rather than increasing its temperature. Now, in this problem, we're told we start off at 40 degrees Celsius, and then we heat up the water until it reaches the phase change point, the boiling point specifically. So the temperature increases first from 40 degrees Celsius to 100 degrees Celsius. Then when it hits 100 degrees Celsius, the sample is completely boiled to the gas phase, all right? And then that's it. That's the information we're given. And then we're asked for the total amount of energy required if that final temperature is at 100 degrees Celsius and we've had that complete phase transition from liquid to gas. Okay, so keeping that in mind, we're going to have to use two equations here to describe the two segments of our heating curve. The first segment is going from 40 degrees Celsius to 100 degrees Celsius. Here we have a temperature change that occurs, and so we would use our equation Q equals mc delta T to describe this first segment. Then we would use a different expression to describe the heat change or the energy change for the second segment where we stay at 100 degrees Celsius, but we have that phase transition from liquid water to vapor. And we're going to use this equation to describe that process, Q equals mL, where L is the latent heat. Okay, now to describe the total amount of energy for this whole process, we can add these two portions together. And so the total energy change, the total heat change, is going to be equal to mc delta T plus mL. And we're given just enough information to start plugging in values. So the mass here, starting off with this first part, the mass is 10 grams. That's what we're given for in the problem. The specific heat capacity of water is 4.18 joules per gram per Celsius. They seem to round it in the problems to 4.2, so we can go ahead and do just that as well. And then delta T for this segment is going to be final temperature minus initial temperature. Final temperature is 100 degrees Celsius. Initial temperature is 40 degrees Celsius. 100 minus 40 is 60. So that's 60 degrees difference for the temperature. All right, perfect. So now we have that set up. That's for the first equation. This is going to be added to the second phase for this process, and that's going to be mL. The mass, again, is 10 grams, and L is something that we're given in the problem. We can use the heat of vaporization of water here, and that is going to be 2,260 joules per gram. And the nice thing about this problem is that we actually don't have to calculate anything because our answer choices are not numbers, they are expressions. And so we just need to find the expression that matches what we just wrote, and that is going to be answer choice C. So we notice our first portion of this expression is our Q equals MC delta T expression, and then the second part is the ML segment for our process. So again, the correct answer for 7 is going to be C. Moving on to problem 8. Problem 8 says, consider the chemical reaction in the vessel depicted in the following diagram. How would you describe this process? A says the reaction is spontaneous. B says the reaction is non-spontaneous. C says the reaction is at equilibrium. And D says there is not enough information to determine if the reaction is spontaneous. Now let's look at this diagram a little bit closer. We have our reactants here. It seems to exist as molecules, and then they get transformed to products. They look like they are individual atoms now. So this molecule has decomposed into its individual atoms. Now, you can gather some information about entropy here. The entropy is increasing because now there are more particles in the system moving from reactants to products. So we can kind of say that the entropy here is going to be positive. Now, enthalpy is a little tricky. We can say that since bonds are breaking here, the reaction should be endothermic, and that means that delta H would be positive as well. Now, if enthalpy is positive and entropy is also positive, what delta G is going to be depends heavily on temperature, and that's some information that we actually don't know. So again, this is going to be a temperature-dependent process if we know delta S and delta H are positive, and again, without temperature, we cannot determine the sign of delta G. If we cannot determine the sign of delta G, we do not know if this process is spontaneous, not spontaneous, in equilibrium. And so the correct answer for problem 8 here is going to be D. There is not enough information. Wonderful. Let's move on to problem 9. Problem 9 says, suppose the standard free energy change of the reaction is minus 2,000 joules per mole for a chemical reaction. At 300 Kelvin, what is the change in Gibbs free energy in joules per mole? Now, this problem asks for the free energy of a reaction at non-standard conditions, and that can be determined with the following equation. Now, we're given just enough information to plug in some values, and from there we can look at our expression and see which answer choice best matches that. We don't have to do any calculations here because we're actually not given enough information to calculate the free energy of this reaction at non-standard conditions. Now we know that the standard free energy change of a reaction is minus 2,000 joules per mole. We also know that temperature is 300 Kelvin. R is the ideal gas constant, and this is going to be equal to 8.314 joules per mole per Kelvin. Remember, we want the answer in joules per mole, so that is the ideal gas constant that we want to use because it has units of joules per mole per Kelvin. So we're going to go ahead and write that down for R, 8.314 joules per mole per Kelvin. And that's going to be multiplied by temperature, which is 300 Kelvin. And then that's going to be multiplied by the natural logarithm of Q. Q is the reaction quotient. We're not given that information, so we're just going to keep it at that natural log of Q. Now that we have our expression, we want to see which answer choice matches it perfectly, and that is going to be answer choice A. Therefore, 9 is A. Beautiful. Let's move on to problem 10. Problem 10 says a chemical reaction has a negative enthalpy. All right, so it has a negative delta H, and it has a negative entropy, so it has a negative delta S. Which of the following terms necessarily describes this reaction? Is it exothermic, endothermic, exergonic, or endergonic? So really quickly, exothermic and endothermic are terms that relate to the heat content of a system. They relate to enthalpy. When we have a negative enthalpy, this indicates that we have an exothermic reaction. This is a reaction that's going to release heat. Whenever we have a positive enthalpy, this indicates that we have an endothermic reaction. This is a reaction that absorbs heat. Now we know that we have a negative delta H, so this reaction is exothermic. But we don't want to quickly omit options C and D just yet. Exergonic and endergonic relate to your Gibbs free energy. Whenever you have a negative delta G, the reaction is spontaneous and therefore exergonic. Whenever you have a positive delta G, the reaction is non-spontaneous and it's going to be endergonic. Now, we're not given any direct information about delta G, but we can kind of insinuate based off of the information on delta H and delta S we're given, because the equation for delta G is delta H minus T delta S. Now we know we have a negative value for delta S and a negative value for delta H. And based off of our conversation in our lecture, when we have a negative delta H and a negative delta S, the reaction could be spontaneous at low temperature, but it can be non-spontaneous at high temperature. Since we're not given any information about temperature, we cannot confidently say that delta G is going to be positive or negative, which means we cannot confidently say if the reaction is exergonic or endergonic. And so we can go ahead and eliminate those answer choices. What we can say confidently about this reaction is that it is exothermic because delta H is negative. And that means the correct answer for 10 is going to be A. Beautiful. Let's do problem 11 next. Problem 11 says, which of the following statements is true of a process that is spontaneous in the forward direction? So let's review a couple of concepts really quickly from this chapter and from the previous chapter. When delta G, when the change in Gibbs free energy is less than 0, then the reaction proceeds in the forward direction. It's spontaneous in the forward direction. Now, when this is the case, Q is going to be less than KEQ. That means the reaction quotient is going to be less than the equilibrium constant. And just as a reminder, the equilibrium constant represents the ratio of the concentration of products to reactants at equilibrium, and the reaction quotient is the ratio of the concentration of products to reactants at any point in time during the reaction. So again, when delta G is less than 0 and it is spontaneous in the forward direction, Q, the reaction quotient, is less than the equilibrium constant. When delta G is greater than 0, then the forward reaction is going to be non-spontaneous. Instead, the reaction proceeds in the reverse direction. In this case, Q is larger than KEQ. The reaction quotient is larger than the equilibrium constant. Now, in this problem, we're asked for which of the following statements is true of a process that's spontaneous in the forward direction. A reaction that's spontaneous in the forward direction is going to have a delta G that's less than 0. Now, when delta G is less than 0, then Q, the reaction quotient, is less than the equilibrium constant. And this is going to match the best with answer choice C. Therefore, 11 is C. Let's move on to problem 12. Problem 12 says, which of the following reactions has the greatest decrease in entropy? Now, as a reminder, entropy is a measure of the disorder or randomness of a system. Generally, gases have a higher entropy than liquids, which have a higher entropy than solids. So, when a reaction produces more gas molecules or moves from solid to liquid or gas, then there's going to be an increase in entropy. When a reaction produces fewer moles of gas or fewer gas molecules, or even moves from gas to liquid to solid, then there's a decrease in entropy. Now let's look at the reactions we're given and try to work through each one to see which reaction has the greatest decrease in entropy. Now for the first reaction, we're going from ammonia, which is a gas, 2 moles of ammonia, to 3 moles of hydrogen gas and 1 mole of nitrogen gas. So we're still going from gas to gas, and we're actually producing more moles of gas. So this is going to be an increase in entropy. That's not what we're looking for. Now for B, we have 2 moles of sodium, solid sodium, plus we have a gas here, chlorine gas, and we produce 2 moles of sodium chloride, which is a solid. Now we're going from solid to solid here, and we're losing this gas. So this is going to be a decrease in entropy. What about C? We're going from liquid, all right, 2 moles of liquid to 2 moles of liquid plus oxygen gas. So here for this reaction, a liquid reactant forms a gaseous product. This is going to be an increase in entropy. So this is not what we're looking for either. Then D, we're going from solid zinc and copper sulfate here, this is an aqueous solution, to zinc sulfate, this is aqueous, plus copper solid. Now in reaction D, each side of the equation has a solid and an aqueous component, so there's approximately no change in entropy here. Now, looking at each reaction, determining if there's an increase or decrease or no change in entropy, the only one that has a decrease in entropy is going to be answer choice B. So the correct answer for 12 is going to be B. Moving on to problem 13. Problem 13 says a reaction coordinate for a chemical reaction is displayed in the graph below. Which of the following terms describe the energy of this reaction? Is it endothermic, exothermic, endergonic, or exergonic? Now, C and D, endergonic and exergonic, these are terms that relate to the free energy of a reaction. If we look at our figure, our y-axis is change in enthalpy and our x-axis is reaction coordinate. We do not have any information on temperature or entropy, therefore we cannot make any conclusions on the free energy of the reaction, and we can go ahead and eliminate answer choice C and D right off the bat. Now our question becomes, well, is it endothermic or exothermic? And in order to determine that, we need to compare the energy of the reactants, what we're starting off with the energy of our products, which is what we end up with. What we see is that there is an increase in energy moving from reactants to products. This describes an endothermic reaction because an endothermic reaction has a higher energy for the products than it does for the reactants. So we can go ahead and say that the correct answer here is going to be A. Again, our reactants are lower energy than our products. So this indicates that the products are higher energy than the reactants, so energy was absorbed during the reaction, and the difference in energy levels between the reactants and products represents the enthalpy change here, and the enthalpy change is greater than 0, hence it's endothermic. Again, the correct answer for 13 is A. Let's move on to problem 14. Problem 14 says the process of melting sodium chloride requires a large amount of energy due to the strong attraction between ions. A researcher finds that 58 grams of salt melts at 1060 Kelvin and it requires a heat input of 30,000 joules. What is the change in entropy? Now remember, entropy is a measure of the disorder or randomness of a system, and the change in entropy, it can be calculated using the heat absorbed or released and the temperature at which the process occurs. So the formula for entropy change is delta S is equal to Q rev over T. Q rev, this is the heat absorbed or released during a reversible process, and T is the absolute temperature in Kelvin. Now we're given both of those information. We know that Q rev is 30,000 joules. That is the heat input required. And then temperature, the absolute temperature in Kelvin here is 1060 Kelvin. So all we have to do is carry out this calculation. Now, if you plug it into a calculator, it's going to be approximately 28.3 joules per Kelvin. Now you have to do this without a calculator, so you can keep 30,000 as 30,000, and then you can approximate the temperature to 1,000, and then 30,000 divided by 1,000, that's going to be 30 joules. That's pretty close to 28, and if you're looking at your answer choices, 30 is pretty close to 28, so you're going to lean towards answer choice A, which is the correct answer. So 14 is A. Now we can tackle our last and final problem. Problem 15 says explosions are necessarily characterized by blank. A says that delta G is less than 0. B says delta H is greater than 0. C says that delta S is less than 0. And D says that T is less than 0. Now, let's break this down. For an explosion, all right, explosions, they release a large amount of energy rapidly. If they're releasing a large amount of energy, then delta H has to be less than 0. It's exothermic. So if delta H is less than 0, B doesn't make any sense because it's claiming that delta H is greater than 0. That's not true. Explosions aren't absorbing energy, they are releasing a large amount of energy. In addition, explosions result in a rapid increase in disorder. So delta S would be greater than 0. So we can go ahead and eliminate answer choice C as well. Now, as for temperature, all right, absolute temperature can never be negative. And so answer choice D doesn't make sense because it's saying that absolute temperature is less than 0. So that's not the correct answer either. The only answer choice that's left is A, and it claims that delta G is less than 0. Now, let me tell you why this is true, not just because it's the only answer choice that's left, but because we can set up our expression for delta G. It's going to be equal to delta H minus T delta S. Now we know that delta S is positive, which means the minus T delta S term is going to be negative. And we also know that delta H is negative. If delta H is negative, this term is negative, delta G is going to be negative, indicating that this reaction is spontaneous. And that is why answer choice A is correct for problem 15. And with that, we've answered all our practice questions. I hope this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day, future doctors.